Sometimes you have a problem like this, where if you were just missing part of it, then you could work the problem out. In this case, if we just had that stuff, we could work the problem out. It's stupid 5's giving us a problem. But if it was just x over that stuff, then a simple u equals, right, would let us work the problem out. So when that's the case, one thing we try to do is break it up into separate fractions. Break it up into separate fractions. Now we're still going to be confronted with this other piece, but at least we can actually handle that, as I'm going to show you. And of course we can already handle this piece. So sometimes breaking a fraction up into pieces can be very, very beneficial as an integration technique. And that's what we're going to do here. So that's going to leave us with two integrals that we have to deal with. And back to 5, I can actually just bring out front. Okay. So first we're going to focus on this piece here, because this is the piece we're more familiar with. We have something over something, and the stuff in the bottom, the numerator is part of its derivative. All right, so we do our basic substitution here. U equals x squared plus 9. Du will call for a 2x to go with the dx. And that's exactly what we need here. Right? That's exactly what we need here. So I can, for this piece anyway, I can divide by the 1/2 on the outside. Right? I'll have 1 over x squared plus 9. And then I can put my 2 with my x dx. So that's going to be 1 over u du. But the integral of 1 over u, is the natural log. So this piece would become 1/2 ln absolute value of x squared plus 9 plus a constant. And then, of course, for the x squared plus 9, we can drop the absolute value. And so that's the first half there. That's the first half. Okay, that's the first half. Now, let's turn to the other part of the problem. So again, the way this worked, we'll let u be x squared plus 9, du is 2x. So we set it up so that I have 1 over u du. I did that by putting the 2 with the dx that I needed, 2x dx that was called for. So I also divide it by 1/2 on the outside. I can then carry the substitution through, 1 over u du. That would become ln of u. So I convert it back to u here. I got 1/2 ln absolute value of x squared plus 9 plus a constant. But because x squared plus 9 is positive always, I drop it. And I get the answer for that first half. Now, for the second half, right now, our only option is to try and manipulate this thing so that it fits the format of an integral that we're used to. Okay, it fits the format of an integral that we know the derivative of. And in this case, because it is something squared plus a number, that is really close to the derivative, or the derivative of the inverse tangent. So I'm going to try to shape this so that I can get it in the format of 1 plus u squared. All right, 1 over 1 plus u squared. That's what I'm going to try to do. Now, towards that end here, this is what we can do. I need to have u squared plus 1. So right now it's plus 9. Okay, so what I do in my very first step is I factor out a 9 in the bottom there. So factor a 9 out of everything. That will make the x squared become x squared over 9 plus 1. Plus 1. Okay, that 9 can then jump outside, and he's going to join up. He's going to join up with the 5. So that'll become 5/9. And then I'm going to have 1 over. And I need a u squared, so I recognize x squared over 9 can be thought of as x over 3 quantity squared plus 1. Okay, that's my denominator. And actually, I guess at this point I can, now that I have that, I can actually drop those 2 parentheses there. X squared, x over 3 squared plus 1. Okay, dx. And at that point, now I can see what I can let u, because I need it to be u squared. I need u squared plus 1. So I'm looking for something to be u, so that's why I rewrote it as that quantity squared, because now I can say we can go in and let u be x over 3 du. We'll call for a 1/3 to go with the dx. And so we can make all those things happen. We can make all those things happen. So since I need a 1/3 to go with the dx, I'll multiply by 1/3 on the inside and divide by 1/3, or in other words, multiply by 3 on the outside. So I'm going to have 3 times 5/9 integral 1 over x over 3 quantity squared plus 1 times 1/3 dx. Okay, so everything's set up. Now I have my u and I have my du, so I can make the transition. And of course 3 and the 5/9 cancels to be 5/3. I have the integral 1 over u squared plus 1 du, which is what I needed for the inverse tangent. So 5/3 inverse tangent of u plus a constant. And then finally substitute in for u 5/3 inverse tangent of x over 3 plus a constant. So that's my second part. That's my second part. And then all we do is put those 2 pieces together. Now they both have a plus c, so those are again just constants plus a constant. So when you put those together, it's just some new constant. So at this point, we then put all of that together. Now let me just go back here and again make sure everything's clear with this one. So the idea is, since I had a square plus a number, that reminded me a lot of the derivative of the inverse tangent. So I'm trying to get it into that format of u squared plus 1. So with that in mind, the first thing I did is I said I need to have plus 1, so it'll be u squared plus 1. So I took the 9 that was in there with the x squared plus 9, and I factored it out. That way I get a plus 1. Of course, to factor it out of x squared, I had to divide it out. That gave me x squared over 9, which I rewrite as x over 3 quantity squared. Of course, bringing that 9 outside. So now I'm ready for the u squared step. So I let u be that x over 3. That's why I had to write it that way. And I can compute my du, which is a 1/3. So I put the 1/3 with the dx and do the opposite on the outside, multiplying by 3. And at that point, I'm ready to become 1 over u squared plus 1 du. And that is the derivative of the inverse tangent. We then substitute in for u to finish the problem off. And now we just put our 2 pieces together here. Put our 2 pieces together here. So the answer becomes 1/2 ln of the quantity x squared plus 9 plus 5/3 inverse tangent of x over 3 plus a constant. So now we've worked out that integral.